Hello everyone, thanks for joining me today. My name is Santiago, a PhD student in geophysics from Argentina and one of the core developers of the Fatiando Terra project. My research is focused on new methodologies for processing forward and inverse modeling gravity and magnetic data. Today, I want to present you the gradient-boosted equivalent sources, a method for interpolating large gravity and magnetic datasets through the equivalent sources technique, developed by Leonardo, Uieda, and myself. The equivalent sources technique is an interpolation method for harmonic data. It consists in defining a set of sources placed beneath the observation points, then estimate their coefficients so they generate the same observed field, and finally compute the field generated by the sources on any other set of points, like a regular grid. This technique has two advantages. First, it generates harmonic fields, and secondly, it takes into account the elevation of the observation points. Its main drawback is that it requires a large amount of memory. Let me picture this problem with an example. Consider a set of data points and a set of sources located beneath each one of them. When we need to estimate the source coefficients, we need to solve this linear problem. The data equals to the Jacobian matrix A times the vector of source coefficients C. If we are working with too many data points and sources, this matrix A might be too large to fit in memory. For example, to interpolate a dataset of 200,000 points, we would need 300 GB of RAM. We developed the gradient-boosted equivalent sources as a solution to this problem, borrowing the gradient boosting algorithm from machine learning. It consists in, first, dividing the survey area in overlapping windows of equal size. Then create one set of equivalent sources per window, and now the data can be reproduced as the sum of the fields generated by each set of equivalent sources. So, the vector containing the data can now be equal to the sum over each set of sources of a step size coefficient times a smaller Jacobian matrix times the coefficients vector of the current set. Notice that we have introduced a new parameter, the step size coefficient. It will play an important role on the fitting process. So, how do we estimate the coefficients of these new gradient-boosted equivalent sources? Let's start with the same example, data and sources. On the first iteration, we select the data and sources that fall under the first window and estimate their coefficients by solving a simple linear problem. Then we predict the field generated by these sources on every point and estimate the step size coefficient for that window. This is done by minimizing the difference between the original data and the step size coefficient times the field generated by the first set of sources. This step helps our algorithm on convergence by incorporating to some extent the effect of every data point outside the current window. Finally, we compute the residuals as the difference between the data and the field generated by this set of sources times the step size coefficient. On the next iteration, we would select the residuals and the sources that fall under the next window, fit their coefficients, estimate the step size coefficient, and finally predict the field on every point and update the residuals. This process is carried out iteratively through every window. We tested our new method against synthetic datasets and arrived to the following conclusions. The gradient-boosted equivalent sources heavily reduce the memory needed to interpolate large gravity and magnetic datasets. We can control the memory usage by changing the size of the windows, and although we found that the best performance is achieved by choosing the maximum window size and that fits into memory. The introduction of the step size coefficient helps to increase the convergence of our method, and we found better performance when the order of the windows is randomized. Using gradient-boosted equivalent sources, we managed to interpolate a ground gravity data from Australia containing more than 1.7 million data points using less than 10 GB of RAM. Here you can see the original data on the left and the interpolated grid on the right with a resolution of 1 arc-minute. And here you can see a section of the original data and the same section of the interpolated grid. If you want to know more about our work, please read the preprint on Earth Archive, which is currently under peer review process in Geophysical Journal International. You can also find out more about our work in the Computer-Oriented Geoscience Lab or visit my personal website. If you want to contact me, please don't hesitate to write me to santiago.r.soler@gmail.com. Thank you.